Hey everybody, welcome back to this week's Physics with Dr. T. We're going to be going through a walkthrough for RC circuits. RC circuits, as you may already be aware, RC circuits are a very useful and versatile type of circuit that can be used for a broad range of options in our electronics world. For example, we can use them as timekeepers. We can also use them for cleaning up signals that come through different electronic circuits and thereby making the signal cleaner more useful. Now the focus of this week's lab is just as much to learn about RC circuits as it is to learn a little bit more about data analysis. But before we get into all that, let's talk about this week's pre-lab activity. For this week's pre-lab, the task is to go out and time your windshield wipers in their motion, which may seem a bit like a silly or what's the point of this type of activity, but I want to remind you the purpose of these pre-labs is to have a simple exercise that can connect you with these concepts outside the classroom, outside the laboratory, so you can recognize them a little bit more easily in your everyday life. And so for this week, looking at the windshield wipers, they oscillate at a regular pace, and that pace is set by the RC circuit contents. And so what you'll do is you'll take a quick measurement of those, and then you'll discuss those, in a short paragraph. Now, suppose that you don't have access to a windshield wiper. It turns out there are a few other options. There are some clocks that use RC circuits to create a rhythmic sound that you hear. We call that an alarm. But the main point here is to recognize these type of things in your everyday life. So you'll write a short summary on this and then turn that in. That's it. That's the pre-lab. Let's move on to the theory. Alright, so let's talk about the theory that lies underneath the RC circuits. It's pretty straightforward. Characteristics of these type of circuits includes a characteristic called the time constant, which is indicated by the Greek letter T, or tau. And this corresponds to the specific time that it takes for the capacitor to either charge up or discharge, depending on what you're doing with your circuit. There are a couple ways that we can extract the value of the time constant of the circuit. One of those is the direct method, where we take the resistance, multiply it times the capacitance, the resistance of the resistor, capacitance of the capacitor, and somehow or another those two numbers come back out with time in seconds. Now, what's actually physically happening when we turn the circuit on? When we close the switch, current starts to flow through the circuit. And early on, there's not a whole lot of charge built up on the capacitors. So current's flowing this way. There's no actual charge crossing the gap. They just get stuck here on each of the plates, the positive side and negative side. But the current continues to flow, and it's very easy for it to do so. So there's not much voltage drop across this capacitor. But as time goes on, they get really crowded. It becomes harder and harder for charge to move into the space because there's been a charge buildup. Positive repels on the positive side, and negative charges repel on the negative side. And as a result, there's a voltage difference between these two sides that is higher than it was before. And this results in a drop in the current, the flow rate of the charges in the circuit. And so, eventually, over time, you have this behavior where the voltage reaches up to some maximum value, whatever you've applied to the circuit. And it follows in this curious way, which is kind of curved. Now, this curve is not a curve that you've worked with in this lab. You may have worked with it if you've had a chemistry or some other chemistry or biology class. And so the way we describe this curve is with this expression here. The voltage as a function of time corresponds to the maximum voltage that you've applied to the circuit times 1 minus exponential, that's what the E is, exponential, negative T over tau, where T is the time as it progresses, and tau, as we just said, is the time constant for the circuit. And now we can come up with a way to get your tau value if you don't know the resistor and capacitor of your circuit. So what you do is you look at the curve and you find where it goes to half the maximum possible value. Whatever the time is at that point, we can plug those values into this expression. When we simplify it down, Vmax divided by 2, that what the voltage is at time, half time, which we call the half-life of the circuit. Vmax, we plug those in, go through the algebra, and we arrive at this expression that says that the time constant of the circuit can also be determined if you know what the half-life of the circuit is, divided by natural log of 2. In this lab, you're going to take the tau using both methods and compare those using percent error. I encourage you to think about why error as opposed to percent difference. Okay, so basically, you're going to walk in, you're going to use equipment that you've used before. Everything's pretty much the same, but I just want to walk through the circuit setup and make sure everything's kind of clear for you. So you're going to start out with the RLC circuit that you've seen in the past. This is the same thing that you've used before, but in this case, we're going to be using the 100 ohm and the 330 microfarad capacitors. So we're going to go ahead and connect it to a power source first and foremost. So we start with our first power in and a black for power out for these two. We want to connect these two and ignore all the rest, so if we put a wire here and a wire here to connect those two, you'll see that they follow the pathway just like you do. Every time you create the circuit, if something doesn't seem quite right, follow the circuit current. So current comes in this way, goes across the capacitor, goes through this, and then down and out through this resistor, and goes back to the power source. So this is a closed circuit on the circuit board. We want to have a switch to control the current flow, so let's go ahead and add the switch in here. Put this in here. Now this one has black, red, red, and really the colors don't matter, just to help you keep track of things. What we're going to do with the red side here, and then we're going to connect another red on the other side, and that's going to go out with the black onto the power source. So that's going to go to capstone. Your circuit's just about ready to go. You want to make sure that you keep your circuit open. You'll go through the settings that are in the lab manual, and finally you'll take the voltage sensor and plug this into your 850 adapter and plug these two ends, put the red on the positive side of the capacitor, the black on the negative side. Otherwise you'll get a negative voltage when you take your data, and there's nothing wrong with that. It just kind of creates a little more challenge when you do the analysis. And that's it. This is what your circuit should look like when you are ready to take data. Okay, so again we're getting into modeling, which seems like it might be a bigger step, but it's actually just an expansion of what you've already done with percent difference, percent error. So what we have is the data here that has been extracted from a previous run of this data. And what we're going to do is we're going to go ahead and go into let's go ahead and create a graph of it. So we go over here to charts, insert chart. We're going to use a scatter plot just like we usually do. And this is just so we can kind of get an idea of what the data looks like in Excel. And remember, if you need to go into Google Sheets and that's where you prefer to work, that's perfectly fine. They should be very similar to what we're doing here in Excel. What we're interested in here is the area in this region where the actual ramping up of the voltage is taking place. So we'll note that the time is taking place right around 1.3 seconds. We'll notice that the maximum value is coming up in this case around 3.98 volts. And so we're going to go ahead and confirm that. So what we do is we scroll down, and what we're looking for is about 1.3 seconds. You'll notice all these data points, they seem so numerous, but they're actually really, really small. It's virtually zero. The system is just picking up noise at that point until you actually see data. So you want to go to the first data point that precedes the actual data. This will be basically zero. So this is our time starting at zero. So I'm going to highlight that in like blue or something like that, whatever color. It just makes it easier for me to find it. If colors don't matter to you, then no biggie. This is just for me to find it. Okay, so this is our starting point. And what we need is we need a new column in here because the time that we have is an absolute time set by the system. But we need a time that starts when the switch is closed. So that's why we're picking this point. So we're going to recalibrate all the times to recognize this as zero. So in order to do that, we right-click on the second column, and we're going to insert, and it's just going to slide in a new column. Scroll down, come down to this point here. This is our zero, remember. In order to make it zero, it's got to be zero. So let me zoom in. So what we'll do is we'll hit equals, always start an equation or a formula with an equal sign, equals this minus itself. But if we try to propagate that formula, it's going to cause mess. So what we need to do is we need to put this as an absolute reference. We're going to put a $sign before the A and a $sign before the row number. That way, this is referencing every cell is going to subtract the value in this particular cell. So hit enter, and you see we get 0. If you move your mouse over the bottom right corner where the little dark black square is, you see, you just double click on that, as you probably know to do by now, and now we've got data that propagates down. It goes all the way down to the very end of the data. And there we have it. So now we can graph that if we want to. We're not worried about that just yet. So this is our time equals 0 point, and we can go ahead and just kind of delete this just because nothing before has any relevance to what's going on once we close the switch, so it's not really important data. So we have our time raw in seconds. We have our time calibrated in seconds. And this is the voltage, channel A, in volts. Now we can graph that. And you just highlight it and page down, page down, page down. And you see how it gets really close, 3.96, 3.961, 3.967, 3.969. And it gets down to a point. Now, I had previously truncated some of this data, so this black bar was here previously. But you go all the way down as far as your data is going, just to go and get there, and we'll insert this graph, and there is the data that you're actually studying. Now this continues on, and it goes down 9.74, 9.75, and on further down until you get to, you see it dropped again, but the maximum value it got to is about 3.97, 3.976, 3.977. And so we can take an average of that and say maybe 3.9765. So let's go back up here. $3.9765. This is important. What you'll have to decide, do you want to use the maximum voltage that you have in your system according to the data, or do you want the maximum voltage, which is your set voltage, which works out to be about 4 volts? And the answer is one that you want to really think about which one is more informative. It goes back to making a decision about how you want to analyze your data. We're going to go ahead and take the value that's in the data set as the maximum. It may be right, it may be wrong. That's something that we have to explore as we go. But what we're looking for, if you remember, is the half time first. So we need to find the time where voltage is half. So V max divided by 2 is this divided by 2. So we're looking for the voltage at 1.988, so we can get to T half. So we come down and we just kind of page down until we find 1.988. We find that data point is right here. We have two possibilities, 1.976 and 2.021. We can take either one of those. Which one is the one that we want to use? Obviously we want to get closer to the actual value, so quick subtraction lets us know that 1.976 is the closer value, so we're going to go take that one as our halfway point. That represents the point when the capacitor is half full. And so that takes place at 0.033 seconds after the switch is closed. So we're going to 0.033. And now we can use the formula on the board, tau, to give us that value, which is going to be equal to this divided by natural log of 2. Enter, and there's your time in seconds. This is what we'd expect the characteristic time of this circuit to be. So now you have Vmax and tau, and you're ready to do the model. So we'll type the voltage model, which is also in volts. We come down, starting here, equals Vmax. You can either type it, you can either click on this and anchor that down with dollar signs, or you can just type the value directly into the spreadsheet, times, beginning parentheses, and then this is going to be 1 minus, you have to type in the word exponential, EXP, you can double click on that. I'm just going to go ahead and manually put a parenthesis there. Negative, we need the time at that particular moment. That's an important part of it. So that goes to this, a calibrated time, divided by our time constant. So we'll close that. But we don't want to hit enter yet, because remember, we need to anchor that, otherwise you'll have some difficulty with the calculations. Again, you can just type the value directly in there, and that saves you a little bit of keystrokes perhaps. Then you double click, and down it goes. We now have a model. So let's highlight the data and go as far down as we can, and now you can see both of those are on there. Quick layout in order to get the axes in place, and now what we need to do is clean up our picture here. So we have data and we have a model sitting on top of the data. And they're not very easy, especially if you print this out. This is not going to be very easy to distinguish. So what is usually done is, for models, you click on the data, you come over here to the marker, and you click on marker options. We want no marker, but we do need a line, so let's turn the line on. Solid line. Let's make it a different color. Let's make it orange again. And you may notice that, well, you can't see the model anymore. Even if we took the data points and made them smaller, take the markers, you can shrink those down by clicking on this pathway and go down to make those smaller. Well, there it is. It's kind of peeking out over here, but it's behind it. So if you right click, you go to select data, and then change the order. All it did was change the order that they're in the data set. Click OK, and now you can kind of see it, but again, it's not standing out. So what do we do? Well, the first question you ask yourself is this good data? Looks pretty good, doesn't it? So here's where the modeling comes in. We're going to ask ourselves if we're quite right. So we're going to create another column that is percent error. Remember, percent error is a percent, so there's not really any units other than percent. Equals open calculation. We're going to take the data minus the theory, close that. We're doing percent error, so we only need to divide by the theory, and I need to put this times 100, so we can just click in the field up here, 100 times. Hit enter. That's going to say div 0 because we're trying to divide by 0 on that particular cell, but highlight the cell again, double click down. We can just take that one away, just delete it. But now we can add this column. But now you have this column, and you can click on the data and go down quite a ways. Chart, add that in there. Again, this is theory, so we want to change this from a data points to a line. Click on the paint can, turn the line on, turn the marker off. Click on none, and now you have data. This is not so easy to look at, so we're going to change that color of that line to, let's say, purple. Why not? And again, you can click on this and quick layout, get your axes on there, and so now you have data you can look at and ask yourself this question: does the model fit well with the data? Does the data match the model? And you can discuss this in your lab report. In this week's lab, this week's lab report is a short lab report, which means it's got the same basic 4 sections. You have your introduction, which contains both the theory and the procedure. You have your data and results, which is simply going to be the output of this now. You don't want to, is the output that you get from here. Now, this one's a little bit of a thinner section because the data is just the data. You do want to talk about how the data came about and if you had any issues when you were setting everything up. You can combine this, for this lab, you can combine your data and results with your data analysis, your analysis section, and combine that. Just want to make sure that it's not just a quick plunk down of the data, here's the data, and move on. In this lab, it's not necessary to have a table of any information. We don't need a sample of the information. There's nothing instructive in that. This is just voltage versus time. You'll have 2 graphs. Graph 1 is going to be your data and theory against voltage versus time plot. And then you'll have a second graph, which will be your percent error versus time. And you can zoom in on that one a little bit more to the interesting area so you can discuss that in your lab report. Remember, as always, to challenge yourself to have some answers for what the data looks like, why the data looks like the way it does. Are there any discrepancies? Did you have to retake any data? And if you did, why? Make sure everybody gets their own data, because even though the data looks identical in each case, there are actual characteristics that you will find and discover are actually unique in each case. So make sure you get your own data. Remember that data analysis is for analyzing the data and explaining why the data is what it is. The discussion section is for zooming out, discussing the lab activity as a whole. What did work, what didn't work, what could be done to make it an improvement, or might there be some other methods that you think would help further explore this characteristic of the RC circuit in greater detail, or modeling in this case. And that does it for this week's walkthrough with RC circuits. I'd like to remind everybody that we have the Physics Help Center over at ID Weeks at the library. And here's our schedule so that you can take a look at when you can drop by that works for you. Until next time, we'll see you guys in the laboratory. Bye. Good? So far so good? Yeah? You happy? I'm happy. Alright, good. Let's do it. We're tiny, we're toony, we're all a little loony. And in this cartoony, we're invading your TV. And just remember, crap. I didn't even write time down. Okay, I've just been BSing on that, I guess, 6 minutes.